Welcome to Sheridan College's Introduction to Instrumentation. This lesson is a part of the temperature module and will be focusing on resistance temperature detectors. After completing this lesson, you will be able to explain temperature coefficients, describe the principal operation of a resistant temperature detector or RTD, describe the construction of an RTD, explain how a Wheatstone bridge works, and explain the purpose of a Wheatstone bridge in an RTD circuit. Let's begin by reviewing Ohm's Law and discussing the impact to Ohm's Law caused by temperature coefficients. A temperature coefficient is a relationship in response in terms of resistance of a matter exposed to a change in temperature expressed as ohms per ohm per degree of Celsius. Simply put, how does the resistance of a material change when the temperature goes up or down? There are two possible coefficients, positive and negative. Negative temperature coefficient, or NTC, materials lower their resistance when the temperature rises and raises their resistance when the temperature lowers. This is useful in electricity for inrush limiting devices like time delay fuses. One drawback, however, is a possible thermal runaway condition, which is possible in some lithium-based batteries or in some semiconductor materials. In these cases, the heat adds to the excitation, and the result is the internal heat cannot escape, and ultimately there's a failure. Positive temperature coefficient, or PTC materials, raise their resistance when the temperature rises, and decreases their resistance when the temperature lowers. Copper and other conductors behave in this manner. As you learned from electrical theory, Ohm's law states the relationship between voltage, current, and resistance, and how in any circuit you can calculate the value of any one of the three if you know the other two. For example, to find resistance, simply divide the voltage by the current. To find the current, divide the voltage by the resistance. And to find the voltage, simply multiply the current by the resistance. This relationship also means that if the resistance changes, then the voltage and/or current must change as well. Keep in mind that a conductor is also a resistor in a circuit. When current flows, it generates heat within the conductor. This then changes the resistance of the conductor carrying the current. Since conductors tend to have a positive temperature coefficient, the greater the heat generated, the higher the resistance of the conductor. The resulting change in resistance and heat means that conductors must be derated in order to prevent failure or fire. Ambient or external heat also changes the resistance of a conductor. The higher the temperature the conductor is exposed to, the higher the resistance. Lower temperatures tend to lower the resistance. Let's look at an example. Let's take a light bulb. Here we have a multimeter connected across an incandescent light bulb and set to read resistance. The bulb is rated at 25 watts and 240 volts. The measured resistance is 173.1 ohms. Let's take the measured resistance and identify it as cold measured. Ohm's power law states that the total power of a circuit is the product of the current squared multiplied by the resistance. So 25 watts would be the current squared times 173.1 ohms. To find the current, we need to rewrite the equation and then square root the result. This gives us 25 watts divided by the resistance of 173.1 ohms, rooted, which gives us an answer of 0.38 amps. We can now check our work, and we find that 0.38 amps squared times 173.1 ohms is indeed our 25 watts. This means that when we give the light some voltage, it should draw 0.38 amps. Okay. Let's rewire the multimeter and put it in series with the lamp and check our current. When we apply power, the light turns on and the multimeter reads 0.101 amps. Well, that's a lot less than we expected. Something is clearly wrong. The meter doesn't present that much resistance to the circuit, so what's happened? Let's go back and check our math. The hot current is measured at 0.101 amps or 101 milliamps. Let's identify that as hot measured. Reapplying Ohm's law, we find the power, when hot, is equal to the current squared times 173.1 ohms. And that only gives us 1.77 watts. That's not even close to 25 watts. What's going on here? Okay, let's start again. Our meter gave us a cold resistance of 173.1 ohms. It also gave us 101 milliamps. It's a good tester, and the batteries are fresh, so it isn't likely the meter. Okay, maybe we should try something different. I mean, Ohm's law is a law, and that means it should always work. Let's look at the hot power again. We got 1.77 watts. Remember that the power law never changes, so that means something else has changed in the output power. If the power changes, then either the voltage, the current, or the resistance has changed. The voltage hasn't changed, so that leaves the current or the resistance. Since the rate of current flow is relative to the resistance, there must be a change in the resistance. Let's work the power formula again, only this time we'll use the hot power, not the rated power. This gives us the hot resistance that is equal to 240 divided by 101 milliamps, which is equal to 2.736 kiloohms, or 2,737.6 ohms of resistance, which is 37 times as much resistance as the cold measured resistance. Ask anyone who has mistakenly tried to change a working lit light bulb, and they will tell you it is hot and will burn your fingers. That means it is producing a lot of heat. This, coupled with the increase of the resistance, clearly indicates that the filament has a positive temperature coefficient. As the temperature rose, so did the resistance. We are now going to apply this knowledge. We're going to take a look at a method that uses the change in resistance due to temperature to our advantage. We're going to use the resistance to determine the temperature. The device used for this is a resistance temperature detector, or RTD. An RTD, or resistance temperature detector, is an electromechanical device that uses the properties of Ohm's law and the impact of applied heat to a known resistance value to determine the amount of that applied heat through the measurement of the change in resistance in the device. At its core, an RTD is a very simple device. It's so simple, in fact, you can make one out of a piece of wood or plastic and wrap a coil of uncrossed copper wire around it. Apply some heat or put it in some cold, monitor the resistance, and you have it, a very crude RTD. But industry and instrumentation need a lot better than crude measurements, so RTDs are highly crafted and laboratory tested for accuracy. The same basic principles of construction apply. A very fine copper wire is coiled around a stable insulator and then covered by a protective heat-conductive metal sheath. They have the end coils lead wires protruding from the end, and it's sealed. Once complete and tested, you have a very precise, directly proportional temperature sensor. There are two varieties of RTD, a 2-wire and a 3-wire. The impact on the number of leads will be discussed shortly. As mentioned earlier, all metals have different thermal resistance properties. RTDs only use positive thermal coefficients, which means again that resistance will increase directly proportional to an increase in temperature and will decrease in resistance with a decrease in temperature. Table 1 shown here shows some of the temperature coefficients of various materials often found in RTDs. Let's refresh our knowledge of Kirchhoff's law. Kirchhoff's law states that the sum of all currents flowing into a node, or a connection, will equal the sum of all the currents leaving the node. This is in keeping with the laws of preservation of energy. Now take a look at this simple circuit made up of 2 parallel legs and 4 resistors. If all the resistors have exactly the same amount of resistance, the flow of current will be the same for both legs, and as Kirchhoff stated, the current returning to the battery will be the same as the current that left the battery. So our circuit is functioning as expected, and the current flow through the two legs are equal. Great. Kirchhoff's law is satisfied and proven. But what would happen to the current flow if there was a short across the two branches? Which way would the current flow? The answer may surprise you, but on careful consideration it makes perfect sense. The answer is nothing. The current flows the same way it was prior to the short. As an electrician or apprentice, you have likely seen the result of a dead short, so this notion of zero change seems counterintuitive at best. But remember one key factor in electricity. You must have a difference of potential in order for a voltage to be motivated to flow in a current. When both branches are identical, there is no potential difference, and as such, there is no current flow across the bridge. This is the fundamental essence of the Wheatstone bridge. Here is the same circuit drawn slightly differently to ensure the two parallel legs are truly the same and an unknown resistance has replaced the short. We know that current will not flow across this resistance if the legs are balanced. But what happens if the two legs are not equal? What happens to the current flow then? Which way does it go? Then regardless of the resistance in the middle, part of the current will flow towards the lower resistance. This was discovered by Samuel Christie in 1833 and was improved by Charles Wheatstone 10 years later, for which the bridge is now named. They discovered that an unknown resistance could be determined by measuring the current flow across the bridge. Let's change the circuit again. Let's replace the unknown resistance with a voltmeter, and let's replace the fixed resistor with a variable resistor. Once this is accomplished, we can monitor the voltmeter and adjust the value of the variable resistor to balance out the circuit again. When the voltmeter reads 0 and shows no positive or negative deflection, the bridge is balanced. Now that we have a basic understanding of the Wheatstone bridge's operation, we can use it in an RTD circuit. Wheatstone bridges are the central circuit used to measure resistance change of an RTD. In this circuit, we have moved the variable resistor R3 from the right leg to the left leg, and we have replaced the variable resistor on the right leg with an RTD. The two resistors R1 and R2 below the bridge are exactly matched. Now, R3's resistance must match the RTD's resistance to have a 0 reading on the voltmeter. The next step is to apply some heat, or cold, to the RTD. The resistance of the RTD changes when heat is applied, and the resistance is directly proportional to the applied heat. When heat is applied to the circuit, it becomes unbalanced, and current will flow across the bridge. In order to determine the new applied heat, we must now adjust R3. By adjusting the resistance of R3, the circuits can be rebalanced. And again, the adjustment of R3's resistance is directly proportional to the change in heat. Once the circuit is rebalanced, no more current flows across the bridge. The resistance of the RTD must equal the resistance of R3, and from this, the temperature is determined by the proportional change of resistance in R3. Therefore, it's a simple calculation to determine the temperature of the RTD. The method used so far has been with the two-wire RTD. The one drawback with this arrangement is that the resistance of the RTD leads is not taken into account, and this can considerably alter the results. Even 1 ohm of resistance will completely alter the results and must be accounted for, or significant errors can occur. A 3-wire RDT adds another lead wire to compensate for the resistance of the lead wires. The two RT leads have exactly the same resistance, and since the two leads are separate legs, they balance out. The current will not flow across the third line and hence the voltmeter. This resolves the leads problem. By now you should have mastered the subtleties of the Wheatstone bridge. Let's move on and look at measuring the resistance to determine temperature. RTDs are accurate and reliable, but they are limited in electrical range or distance, and the signal they produce is not an industry standard. RTDs must be connected to a transmitter. Locally mounted transmitters are commonly used for control. They can have digital or analog 4 to 20 milliamp outputs. The transmitter used in your lab will operate on 0 to 5 volts. An RTD's resistance is a function of the material used in its construction. Since each metal has a different resistance, it's imperative you know what the resistance of the material used in the RTD's construction. Furthermore, simply knowing the resistance of one metal does not help in calculations due to variations between alloys, RTD models, and manufacturer specifications. Every manufacturer carefully measures their RTD and creates tables that show the amount of resistance for any given application of heat. They all ensure linearity, as shown in the graph in the previous slide. Each table that they create will list an alpha value. This is its conversion coefficient and must be used in all calculations. The RTD listed here indicates this is a platinum 100 ohm RTD. This means that at exactly 0 Celsius, the RTD resistance should measure 100 ohms. There's one piece of information not shown in any of the forms, and this is the resistance of the lead wires themselves. This will be important when working on the lab. Let's use the alpha number in this example. The alpha from our example manufacturer is 0.00385. You'll be using a different alpha number in the lab. The formula used to calculate the temperature is the resistance measured minus the resistance at 0 Celsius divided by the alpha times the resistance at 0. This gives us the following. If the measured resistance is 115 ohms, then the temperature would be equal to 115 ohms minus 100 ohms divided by 0.00385 times 100. This then gives us 15 divided by 0.385. When we work that out, the final temperature is 38.96 degrees Celsius. Now let's check that against the table. First, the temperature we calculated is more than 30, so we start there. We find the 30 on the chart, and the next thing we do is we go to the top and left and look and find the 9 column. 30 plus 9 equals 39. Our answer was 38.96. So 39 is the closest we have. Now we're going to go down and cross the 9 column with the 30 row, and we find 115.15 ohms, almost exactly where we started. The last thing that needs to be covered is to always check the leads. When working with RTD and the manufacturer's table, the resistance of the lead is calculated in. However, if you're working with a mystery RTD or working with a new transmitter, the table will be a rough guide until you've done your full calculations. Now I know what you're thinking. Great, more math. Well, this one's really easy. The only difference in the equation is you must expand the measured resistance value to include the lead resistance. And to do that, you simply subtract the lead resistance from the measured resistance and carry it on like before. That's it. That's all. That's the only difference. Now we're going to take a brief look at another electrical thermal detector. It's called a thermistor. We learned earlier in this lesson that a negative temperature coefficient means that the resistance of a device decreases as the temperature goes up and increases when the temperature goes down. An NTC thermistor works on this principle. In practical terms, it can act as an inrush limiter or a safety trip device. At point A, the thermistor is at 0 Celsius. The resistance is 10,000 ohms. This will be seen by the inrush current and will act as a current limiter. At point B, the thermistor is at 250 degrees Celsius. Its resistance is down to 10 ohms. This is practically a closed switch, and therefore this device could be used as a temperature sensor and set off an alarm. If a linear solution is required, a Wheatstone bridge with a resistor can be used to smooth out the curve of an NTC thermistor. The nonlinear characteristics are then compensated for by the modified bridge circuit. Positive temperature coefficient thermistors are resistors whose resistance increases with temperature, like our light bulb example, and decrease with resistance with a decrease in temperature. However, the characteristics are not linear. As can be seen by the graph, the resistance, comparatively speaking, is fairly stable at temperatures below the critical temperature, or TC. Once it reaches that point, the resistance shoots up exponentially. The TC is different for each of the different construction materials used to make the PTCs. Thermistors are available in a variety of shapes, sizes, and switch temperatures. Sometimes they're used in place of motor overloads when built into the motor frame and housing, and therefore can shut down a motor due to excessive external heat as well as overload conditions. In this lesson, we have discussed temperature coefficients, described the principal operation of an RTD and its construction. We examined a Wheatstone bridge and how it works in an RTD circuit. We reviewed the alpha of an RTD and discussed the calculations needed to determine the temperature from resistance. And we discussed NTC and PTC thermistors. You are now ready to watch and participate in the RTD lab. You will find it on Slate. Thank you for attending this lesson.